a coherent motion of clusters that refuses to align with the CMB rest frame, as if the whole observable universe is being tugged the assumption of isotropy. The idea that the cosmos has no preferred direction is one of the cornerstones of modern cosmology. It is baked into the standard model of the universe, the lambda CDM framework, which describes everything from the cosmic microwave background to the large-scale distribution of galaxies. This assumption is so fundamental that most cosmological calculations begin with it, treating the universe as statistically the same in all directions when averaged over large scales. But what if that assumption were not entirely correct? What if there is a subtle, large-scale flow that breaks the cosmic symmetry? In 2008, a group of researchers led by Alexander Kashlinsky at NASA Goddard Space Flight Center published a paper in the Astrophysical Journal Letters that suggested exactly that. They detected a coherent bulk flow of galaxy clusters, moving at speeds of 600 to 1,000 kilometers per second in a single direction. To put that number in perspective, the Milky Way galaxy moves through space at about 600 kilometers per second relative to the cosmic microwave background. Our galaxy's own motion is comparable to this flow, but the difference lies in the scale. The Milky Way's motion is a local phenomenon, influenced by nearby clusters and voids, a kind of gravitational traffic jam on a relatively small scale. The dark flow, however, was observed across a volume of space extending out to 2.5 billion light-years, containing some of the most massive structures in the observable universe. This was not a local anomaly. It was a global motion of a significant portion of the visible cosmos. The detection was made possible by a subtle observational technique known as the kinematic Sunyaev-Zel'dovich effect, a method that requires some unpacking. When the cosmic microwave background photons, those ancient relics from the recombination epoch, travel through a galaxy cluster, they scatter off the hot, ionized gas within that cluster. This scattering imprints a small distortion on the spectrum of the CMB photons, a shift that depends on the bulk motion of the cluster itself. Measuring this shift is like reading a cosmic speedometer. The temperature of the scattered photons deviates from the average by an amount proportional to the cluster's velocity along the line of sight. The team analyzed data from the Wilkinson Microwave Anisotropy Probe, or WMAP, which mapped the CMB with exquisite precision to extract this kinematic signal from 200 galaxy clusters, covering a vast patch of the sky. The result was striking. The clusters were not moving randomly, as the lambda CDM model would predict for objects separated by such enormous distances. In a homogeneous and isotropic universe, large-scale structure should form hierarchically, smaller clumps merging into larger ones with no preferred direction on the grandest scales. The peculiar velocities, or the deviations from the Hubble flow, of distant clusters should average out to zero when you look at a large enough sample. Instead, Kashlinsky's team found that the clusters were all drifting, with considerable statistical significance, toward a 20-degree patch of the sky located near the constellations Centaurus and Vela, or possibly Hydra, depending on the data set. This was not a subtle wiggle. It was a persistent, coherent signal that suggested something fundamentally unaccounted for. The immediate reaction from the astrophysics community was a mixture of excitement and deep skepticism. A coherent flow on this scale fundamentally challenges the cosmological principle, the working assumption that the universe is homogeneous and isotropic when averaged over large scales. If the dark flow were real, it would imply that our entire observable universe, a sphere roughly 90 billion light-years in diameter, is moving relative to something else. This would be akin to discovering that a ship is being carried by a current, even though the ocean floor is featureless and flat. But what could possibly cause such a current? What lies beyond the cosmic horizon that could exert a gravitational pull on thousands of galaxy clusters over a distance of billions of light-years? Several speculative explanations were put forward. One of the most intriguing, and indeed the one that captured the public imagination, was the possibility that the dark flow is a relic of pre-inflationary physics. According to the theory of cosmic inflation, the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. This rapid expansion smoothed out any large-scale curvature and essentially erased all memory of the initial conditions from any one patch of the universe. However, some theoretical models suggest that inflation itself could have been anisotropic, or that the quantum field that drove it left behind a subtle, large-scale directional imprint. The dark flow, according to this line of thinking, could be a kind of fossil, a whisper from the very early universe, a quantum geometry that persisted through the expansion and became encoded in the motion of matter. An even more unsettling possibility was that the flow is being caused by a gravitational influence from beyond the observable universe. Our cosmic horizon is not a physical boundary. It is simply the maximum distance from which light has had time to reach us since the Big Bang. Beyond that horizon, there could be anything: vast structures, massive attractors, or even other bubble universes in the context of eternal inflation. If there were a supermassive concentration of matter or energy outside our horizon, it could pull on the matter within our visible patch, creating a coherent flow. This idea appeals to our existential sense of scale, but it is extremely difficult to test scientifically because we cannot observe anything beyond the horizon. It remains in the realm of speculation, a possibility that cannot be disproven, but also cannot be confirmed. However, the scientific community did not simply accept the dark flow as established fact. In fact, the majority of cosmologists remained highly skeptical, and for good reason. The kinematic Sunyaev-Zel'dovich effect is notoriously difficult to measure accurately. The signal is extremely small, a temperature shift of only a few microkelvin, and can easily be contaminated by other astrophysical processes, such as the Sunyaev-Zel'dovich signal from the cluster's own thermal gas, known as the thermal Sunyaev-Zel'dovich effect, which is much stronger and can mimic the kinematic signal if not properly subtracted. There is also the issue of sample selection and systematic errors in the WMAP data itself. The dark flow signal is a subtle, secondary effect that requires precise calibration. Many researchers believed that the flow was an artifact of data processing or a statistical fluke rather than a real physical phenomenon. The definitive test came in 2013 with the publication of the data from the Planck satellite, the European Space Agency's successor to WMAP, which had far higher sensitivity and angular resolution. The Planck team conducted a thorough analysis of the kinematic Sunyaev-Zel'dovich signal using their own data, as well as a reanalysis of the WMAP data to search for the dark flow. Their conclusion was clear and unequivocal. They found no evidence for a coherent bulk flow at the scale or amplitude claimed by Kashlinsky. Instead, they set an upper limit of 254 kilometers per second for large-scale bulk motions, with 95% confidence. This means that if there is any large-scale flow, it is significantly smaller than the original 600 to 1,000 kilometers per second measurement, or it does not exist at all. This was a major blow to the dark flow hypothesis and seemed to restore the standard lambda-CDM model to its rightful place. The discrepancy between the two teams has never been completely resolved, and that is what makes this story so compelling. Kashlinsky and his collaborator, Fernando Atrio Barandella, did not concede. They argued that the Planck team's methodology for removing the thermal Sunyaev-Zel'dovich effect, which is essential for isolating the kinematic signal, was flawed. They pointed out that the Planck data, when processed with a different set of assumptions and a different mask for foreground contamination, still showed evidence for the dark flow. In subsequent analyses, using a combination of WMAP and Planck data, they continued to detect a coherent motion of about 600 kilometers per second, even as the Planck team reported no significant detection. This is not a case of a conspiracy or a mistake. It is a classic scientific disagreement over data reduction, systematic errors, and the statistical significance of a subtle signal embedded in noisy data. The flow is either present or absent. Both teams cannot be right, but both could have legitimate reasons for reaching their different conclusions. To understand the nature of this disagreement, we have to look at how the kinematic Sunyaev-Zel'dovich signal is extracted. The CMB photons we detect have a characteristic blackbody spectrum, and scattering off a moving cluster causes a Doppler shift, which appears as a specific temperature variation across the cluster. The thermal Sunyaev-Zel'dovich effect, on the other hand, is caused by the hot gas itself, which has a different spectral signature. The challenge lies in separating these two signals. It is like listening for a faint whisper in a room where a loud fan is running. You can try to filter out the fan noise, but the way you do it can distort the whisper you are trying to hear. The Planck team had a sophisticated model of the thermal effect and the galaxy distribution, while the Kashlinsky group used a different approach. Depending on which foregrounds you include and how you handle the error bars, the answer changes. This is not a moral failing on either side. It is the messy reality of doing astrophysics with small signals and limited resolution. Another crucial point is the matter of the clusters themselves. The dark flow signal is based on the motion of galaxy clusters, which are large, complicated structures. They are not point particles. They have internal dynamics, merging history, and hot gas that can confuse the measurement. The original WMAP data used a subset of 200 clusters from the X-ray catalog. The Planck team used a much larger and cleaner sample and also had access to more data. They argued that the dark flow signal was correlated with the X-ray properties of the clusters, which would suggest that it is a systematic effect related to how the clusters are selected, rather than a genuine astrophysical flow. If the flow disappears when you look at a different sample of clusters, or when you change the way you measure the cluster mass, then it is likely an artifact. Kashlinsky's response is that their flow is present even in subsamples, and that their method for correcting for cluster properties is robust. This is a technical debate that has now persisted for over a decade. The scientific process itself is a kind of navigation in the dark. The dark flow is a prime example of how uncertainty is handled in physics. The measurements are difficult, the data are messy, and the human element, the biases of researchers, the choice of statistical methods, the assumptions about astrophysical corrections, all play a role. There is no single experiment that can settle the issue definitively. Even with the Planck data, the door is left open for future observations. The Euclid telescope and the upcoming Vera C. Rubin Observatory are designed to map the dark matter distribution and the large-scale structure with unprecedented detail. They will observe thousands of galaxy clusters and will be able to measure their motions much more accurately than either WMAP or Planck. If the dark flow is a real phenomenon, it will show up again in these new, independent data sets. If it is an artifact, it will fade away as the measurements improve. The truth will emerge, but it may take another decade or more of careful observation and analysis. The universe, it seems, may not whisper in a single voice, but if it does, we are only beginning to learn how to listen. The silence, whether it is a void or a signal, remains the most profound teacher of all.